హాయ్ ఫ్రెండ్స్, ఈరోజు మనం కండెన్సర్ ఎఫిషియన్సీ ఎలా కనుక్కోవాలో చూద్దాం. ఓకే, కండెన్సర్ efficiency. So the condenser efficiency may be defined as the ratio of temperature raise of cooling water of the vacuum temperature, means inlet cooling water temperature. Mathematically consider efficiency that is equal to temperature rise of cooling water divided by vacuum temperature minus inlet cooling water temperature. So that is called, here we get right, T naught Ti divided by Tv minus Ti. Okay, here what is T naught is equal to outlet temperature of cooling water, and then Ti is equal to inlet temperature of cooling water, and then Tv is equal to vacuum temperature. It is the saturation temperature corresponding to the condenser pressure. Okay, now then we are going to see here one problem, simple problem for this. And now here problem 4, the inlet and outlet temperatures of cooling water in a condenser are 27 degrees Celsius and 35 degrees Celsius respectively. Okay, respectively. If the vacuum in the condenser is 700 mm of Hg against barometric pressure 760 mm of Hg. Okay, this is the given problem. So now how to solve this one, we are going to see. This is problem number 4 and solution. Going to write given data. T1 is equal to 27 degrees Celsius, that is coming from Ti. So T naught is equal to 35 degrees Celsius, and now here consider vacuum. So condenser vacuum is equal to 700 mm of Hg, and barometer pressure is equal to 760 mm of Hg. So we know that the pressure in the condenser is equal to 760 minus 700, that is called 60 mm of Hg. So that 60 into 0.00133 is equal to 0.0798 bar. So we go from steam tables. From steam tables, corresponding pressure 0.0798 bar, we find the vacuum temperature TV is equal to 41.5 degrees Celsius. So therefore condenser efficiency is equal to T0 Ti TV Ti, and then that is equal to 35 minus 27 divided by 41.527. So calculate this, we will get the answer in here 55.2 percentage. Okay, so this is the solution part for this, and now we are going to see another one. The following observations were recorded during a test on a steam condenser. So then first one is barometer reading, that is equal to 765 mm of Hg. Condenser vacuum 710 mm of Hg. Mean condenser temperature is equal to 35 degrees Celsius. Condensate temperature is equal to 28 degrees Celsius. Condensate collected per hour is equal to 2 tons. Quality of cooling water per hour is equal to 60 tons. Temperature of cooling water at inlet is equal to 10 degrees. Temperature of cooling water at outlet is equal to 25 degrees Celsius. So then find vacuum corrected to the standard barometer reading. Second one is vacuum efficiency of the condenser. Third one is undercooling of the condensate. Fourth one is condenser efficiency. Fifth one is quality of the steam entering the condenser. And sixth one is mass of air per meter cube of condenser volume. And seventh one is mass of air per kg of uncondensed steam. Okay, this is the problem. So now we are going to see how to solve this one. I know very well. First we are going to write given data. Solution. First I am going to write given. So in this given, first one is barometer reading, that is equal to 765 mm of Hg, and then condenser vacuum is equal to 710 mm of Hg, and then T is equal to 35 degrees Celsius. So then 35 plus 273 is equal to 308 kelvins. Okay, and temperature of condenser is equal to 28 degrees Celsius, and then mass of steam is equal to 2 ton per hour, so that is equal to 2000 kg per hour, and mass of water is equal to 60 ton per hour, so then that is equal to 60,000 kg per hour, and then here Ti is equal to 10 degrees Celsius, T0 is equal to 25 degrees Celsius. Okay, so first we are going to see vacuum corrected to the standard barometer. So this is first one is given. Okay, so now we are going to see how to find this one. We know that absolute pressure in the condenser is equal to, so absolute pressure is equal to barometer pressure minus condenser pressure. So barometer pressure is 765 minus condenser pressure is 710, that is equal to 55 mm of Hg. So and vacuum corrected to the standard barometer reading. So assuming 760 mm of Hg, so then that is equal to 760 minus 55 is equal to 705 mm of Hg. This is the answer. Okay, so here assuming, okay, assume 760 mm of Hg in barometric pressure. Okay, and then we are going to see in here next one, vacuum efficiency of the condenser. So from steam tables, corresponding to the mean condenser temperature Tc is equal to 35 degrees Celsius. So then ideal pressure of steam ES is equal to 0.0562, this from steam tables. Okay, so that is equal to 0.0562 divided by 0.00133, that is equal to here 42.2 mm of Hg. Okay, so we know that ideal vacuum, so ideal vacuum is equal to barometer pressure minus ideal pressure. So then barometer pressure is 765, ideal pressure is 42.2, then it will come 722.8 mm of Hg. Okay, and then vacuum efficiency is equal to actual vacuum by ideal vacuum. So then that is equal to 710 divided by 722.8, that is equal to 0.98 or 98%. Okay, so now we are going to see in here, next one is under cooling of the condenser. Okay, so under cooling of the condenser. So we know that under cooling of the condensate, okay, that is equal to mean condenser temperature minus condensate temperature, that is equal to 35 minus 28. So then 7 degrees Celsius is the answer. And then fourth one, condenser efficiency. Okay, we have already found that pressure in the condenser PC is equal to 765 minus 710, that is equal to 55 mm of Hg. So from steam tables, corresponding pressure 0.073 bar, we find the reaction temperature TV is equal to 39.83 degrees Celsius. Okay, therefore condenser efficiency is equal to T naught Ti divided by Tv minus Ti. Okay, and before we solve this thing, now here substitute that all values in here. 7 TV is equal to 39.83 minus 10. So then this is equal to 0.503 or 50.3% is answer. Okay, so now we are going to see fifth one. What is fifth one is coming here? Quality of steam entering the condenser. Okay, quality of steam entering the condenser. So how much quantity enter into the condenser we are going to find. So let X is quality of steam entering the condenser. So from steam tables, corresponding to a pressure of 0.073 bar. So we find that HF is equal to 166.7 kg, kilojoules per kg, and HFG is equal to 2417.4 kilojoules per kg. Okay, from steam tables corresponding this pressure, you can take these two values, and corresponding to a condensate temperature of T is equal to 28 degrees Celsius, that is called temperature of condensing temperature. Then we take here HFG1 is equal to 117.3 kilojoules per kg. So we know that the actual of entering steam H is equal to HF plus X into HFG, then 0.667 plus X into 2417.4. So you know that the mass of cooling water. So mass of cooling water is equal to MA H minus HFG1 divided by CW T naught minus Ti. So this is called 60,000 is given and 2000 is given. This is H is equal to plus X into 2417 minus 117.3 and then 42.225 minus 10. This is the all value in here. Okay, I just substitute this all value. H is equal to, and CW is given, EMW is given, MA is given. Okay, all values I substitute in here and then solve this thing. Here we will get the sum. X is equal to 0.76. Okay, this is the answer. And now we are going to see sixth one. What is that? Mass of air per meter cube of condenser volume. So mass of air per meter cube condenser volume. And then we know that the absolute pressure of air as per Dalton's law. Okay, as per Dalton's law, PA is equal to PC minus PS. Okay, and then that is condenser pressure and steam pressure. So 0.73 minus 0.0562. Both we know PC value is here. We know that PC value is 1 minute there. I think this is PS. Okay, ideal pressure, and then here is coming from 0.0562 is the PS value. Okay, and similarly we take like that in here condensing efficiency. PC is equal to 0.073. This one also we find it. Look at the problem again. We see that the 0.073 value. That's where it is. So here is PS value is okay. That is no problem. Okay, and then condensing efficiency we need to find here pressure. Yes, this is the from steam tables. We are going to pressure 0.073. this is pressure of condensing steam 0.073. this is for mm of Hg. Okay, we calculate bars, so then this value we can take pressure of condenser kPec. So that this value here we substitute, and then we can find this value is here 1680 Newton per meter square. Okay, I'm going to take this step. So therefore mass of air MA is equal to PA V divided by RT. Then 1680 volume you can take 1, 287 is standard value, so 308 is given. So we can solve this thing, we'll get the answer here kgs. Okay, that is the mass of air. And the last one, mass of air per kg of uncondensed steam. Good. So mass of air per kg uncondensed steam we need. So here also we go first from steam tables. From steam tables, corresponding temperature T is equal to 35 degrees Celsius. That is mean temperature, mean condensing temperature TC, and then specific volume of this Vg is equal to 25.245 meter cube per kg is coming from steam tables. Thus, air associated with 1 kg of steam at 35 degrees Celsius will occupy the same volume, that is 25.245 meter cube per kg. So then MA, therefore mass of air is equal to PAVG divided by R into T. So we are going to simply substitute 25245. Before we know 1 kg, but here we take some amount 287 into 308. So that's coming from here 0.48 kg. This is the answer. Okay. So this is the procedure to solve the condensing problem. And tomorrow we will see in next class source of air into the compressor. ఓకే సార్ కండెన్సర్లోకి మనం ఎయిర్ అనేది ఎలా పంపిస్తామో అటు సోర్సెస్ ఏంటి అనేది మనం నెక్స్ట్ క్లాస్లో వీ విల్ డిస్కస్. ఓకే, థ్యాంక్ యూ.